Ding. All right, so the record is on. So this is the only last two pieces that I need to go over in terms of the signed versus the unsigned interpretation of a bit pattern. This is pretty much at the end of the reading module. Um, I certainly hope that you guys at least got a chance to read the reading module and kind of look at these and go like, yeah, yeah, I kind of know what it is. So I'm just gonna go over these, for a very short amount of time, and then we're gonna move on to binary comparison today. So VUXW is the unsigned interpretation of a bit pattern X up to W bits, and we want to know what the value of that interpretation is. So that's why it's called VU of XW, and it is in the sigma notation. And if you recognize this sigma notation and go like, oh, but this is really just a special case of base conversion, that's exactly where it came from. Okay, so there's no big secret about VU XW. Now VS XW is the sign interpretation or the value of the sign interpretation of a bit pattern X up to W bits. So you can see these two are almost exactly the same except for one thing. In the case of unsigned interpretation, we go all the way to the most significant bit, which is bit W minus one. But in the signed interpretation, the sigma only goes up to the second most significant bit. So what do we do with the most significant bit? The most significant bit, or bit W minus one, is also multiplied to 2 to the power of W minus 1. In other words, the quantity or the power of 2 that is associated with the most significant bit is not changed. The only thing that we change is instead of adding it to the rest, we are subtracting it from the rest. So that's the only difference. So these two definitions can be helpful in order for you to understand, okay, if I give you a certain bit pattern and I say interpret this bit pattern as either unsigned or signed, this will give you an idea of how to do it. All right. So that's the very last piece about signed versus unsigned interpretation. So after that, we are moving on to binary comparison. All right. So binary comparison starts with a little section that talks about only less than is needed. This is because with only less than, we can actually figure out all of the other comparisons. And to illustrate that, oh, I can do this. This is Joplin, and I'm really glad that most people in this class have a little notebook, paper or otherwise, or have a computer in front of them so that they can take notes. Now, am I forcing you guys to take notes? No. Am I going to take your notes back and evaluate whether you're taking your notes correctly? No, because I don't even know what is correctly from your perspective. Everybody is going to take notes in a different way because you'll be all taking information in a different way. But just having a paper-based or computer-based or device-based way to take notes available means that, oh, you just got an idea, then you can jot it down. Okay, it is yours. So I'm glad to see people are starting to do that. All right, so getting back to Joplin. Joplin, if you don't know what Joplin is, it is okay, it's better for me just to show it, okay? So I'm going to the CISP 310 folder, and I'm just going to create a new note here, okay? So in a certain way, it is a note-taking mechanism, but it is something that require a little bit of, um, you know, getting used to. So let me illustrate what I mean by getting used to. On the left-hand side here, I can type in Markdown, which is a pretty much plain text format, but it can also be formatted, into very nice HTML. So the left-hand side is what I actually type, which is, really just plain text. On the right-hand side, it is going to be the HTML rendering of the Markdown thing. So one thing I can do is to say, pound is starting a heading. So I can say, in this case, y less than is all we need. Okay. And you can see on the right hand side, it is rendered in HTML. So now I can enumerate all the operators. So now I can say, okay, what about less than itself? Well, less than itself is easy. Okay, x is less than y. Oops, is just that. Okay, because we have less than, so we can say x is less than y. We can confirm whether x is less than y. What if we have x is greater than y? Well, we can just flip it, right? It is the same thing as saying is just y is less than x. So just by reversing the order of the operands, greater than is really the same thing as less than. No big deal. So now we get into something that is a little bit more hairy. Okay, x is less than or equal to y, but that is really just the negation of y is less than x. So this one might take a little bit of time to absorb it. Are you getting it? Okay. If I say that x is less than or equal to y is true, is that saying the same thing as it is not the case that y is less than x? Okay, now it is important to include the equal to. So in other words, if x does equal to y, is it also true that it is not the case that y is less than x? Okay, because we have to make sure the boundary case is also covered in this case. All right, so the next one is really just the reverse of this or the flip side of this. Okay, so this is just your y is, oh, sorry, x is greater than or equal to y. Then you already know the trick. We just kind of flip the whole thing and we say, okay, that's an easy one, okay? Because compared to the previous one, all we have to do is to switch the order of the x and the y. So now we get into something that's a little bit more hairy, which is what about x does not equal to y? Okay, in C++, it is the exclamation point equal to. There we go. Well, as it turns out, this is not too hard, okay? This is really just, x is less than y or y is less than x. So if I can use Boolean operators or logical operators, and I also just have less than as a comparison operator, also known as a relational operator, I can just re-express x that's not equal to y as x is less than y or y is less than x, because in either case, x and y are not the same. Okay, and then the last one is equal to. Okay, so how do we express equal to? X equals to y. So that one is just, okay, and I'm going to be super lazy here. I take this whole thing and just negate it. Put a gigantic negation in front of the whole thing. That's it. So if you look at, you know, um, these six relational operators, you can see how we can just use a logical operator or several logical operators combined with the less than relational operator, and we can recreate all of the other relational operators. Are we doing okay so far? All right. So in theory, less than is all we need. It is quote unquote I guess you can call that the universal relational operator, because with that we can derive all of the other ones. All right. So this is Joplin. Okay, I'm just illustrating what Joplin can do because you can type, and if you know how to do LaTeX, it is also really great with entering math equations. So if I want to recreate VS and VU, we can now say, okay, with a dollar sign, you start the equation. So V underscore S is a subscript, and then in parentheses X and W. You don't have to write this down. I'm just really just playing with it right now. So you can say the summation where I starts from 0 and I ends with n minus 1, or W, sorry, W minus 1, minus 2 actually. And then we have x underscore, because we are extracting a particular bit, it is x subscript I times, okay, if you want to emphasize the times, you can use C dot or center dot. And then the other one is going to be 2 to the power of I. And then the whole thing, you have to subtract x underscore. And then this time we have to use braces because it has more than one thing in it. So that would be w minus 1, and then times 2, c dot 2 to the power of w minus 1. like so, and then another dollar sign to end the whole thing. So now we have the math equation. Yep. Question? Xi. Oh, times. Yeah, you're correct. Not Wi. It is 2 to the power of I. Thank you. Right here. Thank you. But you can see, you can use text here on this side to enter a crazy math thing over on the other side. You can also do integration. You can also do chemistry, symbols, and all kinds of stuff like that. So I'm just exposing Joplin as a potential tool for you to kind of take your notes. And for those of you who go home, look at your handwritten notes and go like, okay, I want to refine this to something that I can actually keep and put it on my computer. That would be one way to do it. So as you go over your own notes that you handwrite during the class, and you go like, okay, I want to expand and also, kind of relate this to the class material and whatnot. I think this is a pretty cool tool to learn how to use. Markdown is a really useful format. Why? Discord, yep, and also strike out. Okay, you can do strike out and all the kind of like, oh, because I guess Markdown is not easy for a layman to understand or to learn. But for you guys, you already learned C++. Okay, what is Markdown compared to C++? Nothing. I tell you, it is nothing. So, and also, if you use GitHub, how many people at least know what GitHub is? Okay, so when you go to the README of a GitHub project, it is all entered or typed in Markdown. So that means that if you want to start a GitHub project and you want to have a really fantastic looking README file, learn how to use Markdown. Okay, because once you learn how to use Markdown effectively, you can have a really nice, good looking, organized README file for your own GitHub projects. Okay, so Joplin is free. It's open source. You can pay money to subscribe so that you can actually save your notes online. So you can go to synchronize. I don't do that. I don't subscribe. I just save it locally, which is perfectly okay. All right. So just a little exposure of a tool that I have used personally to kind of just experiment with things and also to capture in-class notes, also. So this is just kind of cool. All right. Cool. So now we move on to how to compare, how to confirm whether a number is less than another number in binary. And we start with something that is like, Tag, but we just mentioned this. Yes, we just mentioned it too, um, which is what is VU and also what is VS. Okay, so both of those are just repeated here. There's nothing new here. Okay, these are exactly the same definition as we have just talked about from the signed versus unsigned interpretation. It's just a repetition just so that people start with something that is helpful when we are looking at values. Are we doing okay so far? All right. Any questions up to this point? So what do you do with these definitions? If you are handwriting or if you're organizing these definitions, put all the definitions to one place, okay? Because that makes it easier for you to look up. And in an exam, you won't be flipping a crazy number of pages just to find a certain definition. So, um, so you have been warned. All right, so we're going to take a look at unsigned less than. In other words, using the unsigned interpretation of a bit pattern, how do we confirm a number is less than another number? So the green box is something that I did last semester to emphasize on if you have to skim, do not skim the green boxes. Skim everything else except for the green boxes because the green boxes give you the summary of what you actually need. So that means I really have to go over what the green boxes are saying. in a binary subtraction of two m-bit patterns, x minus y, so x is a bit pattern, y is a bit pattern. Tm, so because the two numbers are m bit wide, so m is the number of bits for both the xy and also the difference. So Tm, or t at position m, equals to 1 if and only if the unsigned, the value interpreted unsigned of xm is less than the value interpreted unsigned of ym, assuming t0 is a 0. All right, what does that mean? Can we use some examples, right? Okay, so I'll give you some examples, but you have to kind of look at the examples and you go like, okay, am I really understanding what this statement is saying? Okay, so you have to make the connections. I will try my best to give you an idea of what it looks like. Yes, this is a custom screen when my tablet is sleeping. Your SuperNote is sleeping, so not anymore. Wake up. There we go. Oh, it won't wake up. Hmm. All right, fine. We'll just reconnect. We go refresh, and I think we're still good. There we go. All right. So I'm going to give you two examples. And one is less than, and the other one is not. So we're going to start with something simple. 1011 uh, versus, so this is x, versus 0110. Okay, I'm just randomly picking two binary numbers. Okay, so in this case, what is VU 10114? What is that? What is the unsigned interpretation of 1011? This is straight up base conversion. So let me emphasize this is a base 2 number. Okay, I know some of you know how to do this, okay, because I just showed you the equation. So what I'll do, I'm okay with awkward silence. So I'm just gonna wait. So what is the answer here? It's 11. Very good. Okay, because it is 8. Sorry? Nope, it is 11. So 8 plus 2 plus 1, which is 11. So don't be scared of being wrong, okay? Because being wrong is actually good. Because if your answer is wrong, it means it reflects maybe you did not understand base conversion correctly. It's better to know why or what you have misunderstood at this point of time rather than in the test, because in the test it's going to cost you points. So being wrong is actually a good thing. Now, being wrong or making mistakes and not learning from it, that may not be very productive. Okay, but making mistakes and learning from the mistakes, I think those are one of the best ways to learn. Okay, is to make mistakes, realize what the mistakes are, and then learn from the mistakes so the same mistakes do not repeat. Okay, that is actually one of the best way to learn things in the class. It's a different thing when you're driving on the highway. Okay, so don't quote me when people get into a car accident. It's like, but Tech said it's okay to make mistakes. No, that's very specific to a class like this in the calculations, because some people can take it to the extreme. It's like, but Tech said. Yep. I'll be surprised if you guys remember me after you graduate. So I think I'm pretty safe there. All right, cool. So what about the next one? VU with 0110 in base 2 and then the 4. So that one is just 4 plus 2, which is 6. Okay, so now we ask the question, is x less than y? X is less than y. The answer is nope, it is false because 11 is not less than 6, right? Yes, yes. interpreting up to 4 bits. In other words, the bit pattern itself can be longer, but we only interpret up to 4 bits in this case. So you might ask, why do we have to specify how many bits we're interpreting? It's because in, I think, one particular theorem, I actually need to rely on we're interpreting up to this many bits, even though the bit pattern is longer. Yep. hmm All right. So this part here, we kind of know, okay, we do the base conversion, and then we confirm that, yeah, what about T of M? What is M in this case? M is the number of bits that we're dealing with for the numbers. So what is M in this case? M is 4. Okay, very good. So now we want to look at T of 4 and see whether it is in fact a 0. Okay, because we said that T4 in this case is a 1 if and only if x is less than y. So that means if x is not less than y, then T of 4 should be a 0. So we want to confirm that. All right, so we're going to go for the full version of subtraction just so that you have another practice of how to do this. And I'm going to use the bitwise operations, or I'll explain this using the bitwise operations. Q is the exclusive OR of the x and y of the same column. So this is a, whoops, I just, this is a 1, 0, 1, 1. And we already said that we can assume T0 is a 0. So now we just have to work out all the T bits, okay? 1 minus, or 1 not 1 and 0 is a 0. Not 1 and 0 is a 0. 0 or 0 is a 0. I'm using the bitwise operation for the borrow flags to compute the borrow flag of the next column. So now we have, right, so we have not 1 and 1 is a 0. Not 0 and 0 is also a 0. So now we have 0 or 0, which is also a 0 here. Not 0 or not 0 and 1 is a 1. Not 1 and 0 is a 0. 1 or 0 is a 1. And then finally, we have not 1 and 0 is a 0. Not 1 and 1 is also a 0. 0 or 0 is a 0 here. Now, technically, we don't even need to know the difference because the only bit I need to know is T of 4 in this case, which is this flag here. This tells me that x should not be less than y. So it is already confirmed. But just for practice, I'm going to finish up the last row. So D is the exclusive or between the Q and the T of the same column. So this is 1, this is a 0, this is a 1, this is a 0. Does that make sense? 0, 1, 0, 0, 1, 0, 1 is a 5. 11 minus 6 is also a 5. So, just a quick sanity check means, okay, I probably did everything correctly. So do we have any questions about this particular example? The left-hand side, the actual binary subtraction, that's stuff that we have done already. Okay, there should be no surprises or unknown to the left-hand side. The right-hand side is what we're trying to learn now, is how do we know, how do we confirm that x is in fact less than y? How do we use T of 4 in this case as an indicator of whether x is less than y? So I'll give you another example. Okay, the other example, we can just flip those two around. Okay, 0, 1, 1, 0 minus 1, 0, 1, 1. Okay, and I'll do this really quickly this time. So I'm not going to spell out the actual operations. All right, does that seem right to me? Nope, that doesn't seem right. What did I, where did I make a mistake? Okay, this is exclusive or the previous one. Okay, that is correct. There's a borrow here. Oh, okay, I know. That should be a borrow here too. There we go. So this should be a 0. All right, so let's see whether this makes sense or not. So in this case, VU x4, okay, because this is x, is the 6. VU y4, this is y, is our 11. So 6 minus 11 is, in this case, it says it is 11, but with a borrow of 16. So I think that is correct because, yep, because 11 minus 16 is negative 5, which is 6 minus 11. So I think everything works out. But the rest of the calculation is actually not super important. All I really want to know is whether t of 4 is a 1 in this case. Because the statement that I mentioned earlier in the green box says t4 is a 1 if and only if x is less than y in the unsigned interpretation. And this example also confirms that. So are we doing okay so far? Understanding what the green portion that I was referencing earlier actually mean. In other words, we're looking at this green box here. I'll close the other window, which is not needed. Are we good with this? All right. So, okay, that is kind of cool. So what about section 3.1? It is a proof, okay? So if you do not know what is proof by induction, you probably cannot understand this yet, okay? On the other hand, if you took CISP 440 already, and you know what is proof by induction, this is an example of proof by induction, okay? So if you have taken CISP 440 already, this is a good test to see whether you can apply proof by induction. So for this class, if you don't know what is proof by induction, you can ignore the entire section 3.1. So that means we skip a whole big chunk of code here, and then we move on to signed interpretation. Yes, it is not really difficult to understand. You can probably just do a Google search, and Wikipedia probably has a really good explanation of proof by induction. You can also ask ChatGPT because this module is already uploaded to ChatGPT, so maybe it already has the ability to explain. It will explain the actual proof along with the principle of proof by induction at the same time. Yep. All right. So what about sign interpretation or comparison involving sign interpretation? So that is a little bit of a mixed bag. Okay. So we are going to go with the easy part first. So the easy part is to say, okay, this is the easy part. Um, so, okay, so assuming the signed value of x and the signed value of y, are just, interpreted as x and y. So if x is indeed less than y, then x minus y is going to be less than 0. Okay, so does everybody understand why this is the case? Because all we have to do is to subtract y from both sides, okay? So if we subtract y from the left-hand side, it becomes x minus y. When we subtract y from the right-hand side, y minus y is a 0. So this inequality becomes this inequality, okay? So because of that inequality, anything that is less than 0, the sign bit is going to be a 1, which means bit m minus 1 is going to be a 1. So we might think, oh, this is all we need, okay? If d of m minus 1 is a 1, then we can make a conclusion that the sign interpretation of x up to m bits is less than the sign interpretation of y up to m bits. Okay, so this is a direct mathematical observation, and it does work up to a certain point. Okay, so I'm going to emphasize that it's only working, but up to a certain point. So we're going to use the same two examples that we looked at just to see how that works. Okay, so let me get back to my tablet. Okay, so what I'll do is I'm copying the left-hand side to the next slide and leaving the right-hand side here. So let me use the lasso tool. Okay, and just take this chunk and copy that. Go to the next page paste over here, position it the way I want, which is here. Excellent. So now I can talk about the sign interpretation. So what is XS, VS, sorry, VS X4 in this case? You can see how I'm immediately using the definition that I used a little bit earlier. So that means if you wrote it down or if you have it on your screen, it'll be super helpful because now you know, oh, okay, VS X4 is really just looking at, we have a 1 plus a 2, no 4, but we subtract the 8 from the rest, okay? So this would be 1 plus 2 minus 8, which is a negative 5. Is that okay? This is a direct application of the definition of VS as defined a little bit earlier. So what about Y? Y is a little bit easier, okay? Because we don't have anything, we don't have a 1 at the most significant digit. So this one is really just the same as before, which is 2 plus 4, which is a 6, okay? So now we look at the sign bit, okay? This is our sign bit over here. You go like, tech, it's not working because negative 5 is in fact less than 6, but the sign of the difference is a 0 and it's not matching the description. Okay, so we'll take a look at this and say d of 3 is a 0 in this case, and then we'll go like, what the what the, what is happening here? Okay, so we'll go like, okay, this needs a little bit of explanation. We need to take a look at this. We'll look at the other one too. So in the other one, we just flipped the x and the y. So I'm just going to do a really quick one. So this time VS x4 is a 6. VS y4 is a negative 5. So once again, this time d of 3 is a 1. We go like, what? Because I thought we are supposed to see d of 3 being a 0 in this case, because 6 is less than negative 5 is false. Okay, so a little bit of a mystery here. Then we go like, okay, but Ted, can you show me an example where the sign flag of the difference actually tell us about whether x is less than y? Okay, sure, it's easy. So we can say 0, 0, 0, 0 minus 0, 0, 0, 1, okay, and 0 minus, so I'll do the whole thing. So we got a 1, 0, 0, 0 here for the q, and then we have 1, 1, 1, and also a 1 over here. And then the final result is this. So this is the binary subtraction of 0, 0, 0, 0 minus 0, 0, 0, 1. But what we are really interested in is this is x, this is y, so and this is d. So we want to go like, okay, what is v as x4? I think this one is pretty easy. 0. Very good. And what about v as y4? That's also really easy. It's just 1, right? So 0 is less than 1 is true, right? But we look at the sign flag of the difference, it is also 1. Okay, so this one has dm being a 1 when x is in fact less than y. We flip the order of those two. Okay, now this time we have 0, 0, 0, 1 minus 0, 0, 0, 0. This is also a super duper easy subtraction because there are no borrows of 1 whatsoever in this one. So we have a 0, 0, 0, 0 here, and also a 0 here, 0, 0, 0, 0. So this one has a sign flag, or the difference of the sign flag of the difference is a 0. Okay, so this time it is consistent. 1 is less than 0 is false, and dm is, or dm minus 1, sorry. This is minus 1 because it's the most significant bit of the difference is a 0 in this case. So what is going on here? What do you think is going on? Because every subtraction should be more like this, where the sign flag of the difference should be a 1 if and only if x is less than y, and it should be a 0 if x is not less than y. So what happened to the previous case? Yes. Nope. If one of them has to be a zero, then you only have a very small number of cases in which it will work. So it's not quite like that, okay? But it's a good observation. I just chose this as an example. So if you are to compare two and three, it would be the same. So if x is 2 in the first example and y is 3 in the first example, it will work out just fine. Okay, so let's go back to the previous page. Okay, we go back to the previous page and then we try to interpret what is going on with the difference. X is negative. We are subtracting a non-negative quantity from a negative quantity, and yet D is non-negative. How do I know right away that D is the sign interpretation of D is non-negative? How can I tell right away? Because the most significant bit is a zero. So in return, okay, so I'm going to chase down the reasoning here. Why can I tell that the signed interpretation of a bit pattern has to be non-negative if the most significant bit is a zero? It goes back to the definition of VS. What is the definition of VS? What do we do with the most significant bit? Yep, the most significant bit tells us whether we should subtract the power of 2 corresponding to that position. Everything else are added. So that means if the most significant bit of a bit pattern is a 0, there is no way VS can end up negative. Does that make sense? I intentionally did not show VS on the screen as I'm talking about this because I'm trying to see if you guys have written down the definition of VS and you guys are just going down to your own notes. It's like, oh, okay, right. Okay, that's exactly what it is. That is also a reason why you need to take notes, okay? Because when you're in a lecture, many times I will refer to things that I have just talked about. So having it written down on a piece of paper or on your own device is going to help you because now you can reference back to what I have just talked about. Okay, but I'll be kind and kind of show you what we have talked about before. So this is the definition of VS right here. And you can see that x of I can only be 0 or 1, which is not negative. 2 to the power of I are powers of 2, which cannot be negative. So none of these terms in the sigma can contribute to a negative value. The only time you can end up with a negative value is because you're subtracting this non-negative value. But this product can only be non-negative, can only be negative if and only if x of m minus 1, which is the most significant bit, is a 1. And that's why x of m minus 1, or the most significant bit of a bit pattern, is also known as the sign bit. Because if that bit is a 1, then the number has to be negative. Okay, wait. I just said something that you should not just swallow like, oh yeah, if text says so, it is so. Okay? What did I just say? I said anytime the most significant bit, which is x subscript m minus 1, is a 1, the whole thing, this entire thing, the sign interpretation of the bit pattern x up to m bits, that whole thing is going to be negative. So why do you think that is the case? Because we do have a sigma of a whole bunch of stuff on the other side. Why is it not possible for the sigma to be at least as much as the negative quantity? Yes, but it's being weighed against all the little ones added together. So I'm asking, why is the quantity of the most significant bit itself is already guaranteed larger than the summation of all the less significant powers of 2? So you can make an observation. Okay, yes, go ahead. hmm But why? I'm asking why is that the case? Mm, okay, so let me illustrate what I mean by that first. Okay, so it is a mathematical question. Okay, but nonetheless, it is a question that I think if I were you, okay, on the other side, I would have asked that question. It's like, how do we make sure that the sigma is not outweighing the one single power of two that is now specifying a negative quantity. So we'll make some observation, right? Okay, so let's look at two bits. Okay, there are only two bits in this number. This is bit 0, so it can only contribute up to 1. This is bit 1, which can contribute a 2, so it go like, oh yeah, 1 is less than 2. Okay, so now we look at 3 bits. So when you look at 3 bits, we have 1, 2, and 4. So the 4 is greater than the 1 plus 2. Okay, then we look at 4 digits, 1, 2, 3, 4. 1, 2, 4 versus the 8. Okay, the 8 is still 1 larger than 1 plus 2 plus 4. But this is really just a pattern. It is not a proof in any way. So if you're thinking, hmm, this is kind of interesting. So how do I prove that no matter how many bits we are looking at, the largest or the most significant bit or the power of 2 corresponding to the most significant bit is basically the contribution of everything else plus 1. It is not calculus. This is also calculus is useless in this class. Yes, I just said that. You can tell your math professor about it. Um, so it has to do with proof by induction again. Okay, so you start with the base case, and then you go like, oh, okay, now we can make an assumption that it works up to this case. We just have to prove that it will also work for the next immediate case. That's the best way I can describe proof by induction in a single sentence. So that is a very powerful technique in proof related to mostly programming. Okay, it is useful in general math as well, in linear algebra and many other types of math, but in computer science, proof by induction is of superb importance because of recursion. Okay, so recursion is a programming style, it's a way to write programs. It corresponds directly to the mathematical proof technique that we call proof by induction. I'm not going to get too much into that discussion in this class, but I hope it will also set up a certain kind of like an expectation of what you will learn in CISP 440, especially if you take 440 here at ARC. Because I know the other colleges they teach CISP 440 in a different way. The reason I know why I know how 440 is taught here is because I teach it here. All right. So, but we can actually come to we I cannot prove it, okay? Not in this class, but I can show you that if the most significant bit is a 1, it guarantees the sign interpretation of that bit pattern is going to be negative. The only question is how negative does it go? Is that okay? Go ahead. Okay. Okay. I thought you had a question. Nope. Okay. All right. That's all right. Okay. So let's go back to the cases where it did not work. Okay. So this is where it did not work. So what we want to do in this case is to ask the question of, okay, so if I look at the signed interpretation of the difference, okay, what is that going to be? Okay, so in this case, you can see it is really quite easy because the most significant bit is a 0. We know it is not negative already, which is already wrong because we are taking a negative quantity, which is x, and we take away a non-negative quantity y from a negative quantity. We should end up with a negative number, but we did not. What we ended up with is just 5. So in this case, the signed interpretation of 0101 is a 5. Does that make sense to you? Negative 5 minus 6 is 5. No, it should not make sense at all. So what is happening here is negative 5 minus 6 is negative 11. Okay, that is the correct result, right? So go back and check your number wheel for 16 slots or 4 bits and see if negative 11 is on one of those slots. It is not. The most negative value is a -8. In other words, we have an overflow situation. The result of the subtraction in this case is specifying a quantity that we cannot represent using only 4 bits. It is called an overflow. Okay, so now we go like, oh, okay, so if we are to track whether we have an overflow situation, that's an overflow. Okay, what about the next case? Okay, if you look at the sign interpretation of D in this case, what is it? Well, it would be 1 plus 2, which is a 3, minus 8, which is a -5. Does that make sense to you? 6 minus -5 is -5. Nope, does not make sense. The sign itself alone does not make sense, right? So why is it happening? It's also the same thing because 6 minus -5 is positive 11. So you look at that particular wheel and you ask, is 11 one of the choices in the signed interpretation? The answer is no, because 11 is actually, I mean, the bit pattern of 1011 is used already to represent -5. It cannot be representing -5 and 11 at the same time. So we have an overflow situation again in this case. Is that okay? So if you're thinking, if there's an overflow situation, then we cannot rely on the sign bit of the difference. You are correct. Okay. Every time there's an overflow, which means the actual difference is out of range of 4 bits in this case of what we can represent using 4 bits, then we have an overflow situation. And whenever overflow happens, the sign bit of the difference cannot tell me, it will give us the reverse of what it is supposed to be. On the other hand, if we look at this case, it is not an overflow. Okay, 0 minus 1 is in fact -1, which is also in this case V as D4 is just -1 because it is 1 plus 2 plus 4, which is a 7, minus the 8. So it is just -1. Does the sign make any sense? That you subtract a non-negative quantity from a non-negative quantity, ending up with a negative quantity? It can happen. It may or may not happen, right? Because when you have 2 minus 3, it is negative. When you have 3 minus 2, it is not negative. So the sign flag of the difference can be either way in this case. So we have overflow being a 0 in this case because we do not have an overflow situation. The bottom one is basically the same thing because it is pretty easy to see the Vs of D4 is really just, oh, I made a mistake here. That's supposed to be a 1. It's just 1, okay? So this time we have a non-negative, we are subtracting a non-negative quantity from a non-negative quantity, ending up with a non-negative quantity. Can it happen? Absolutely. So in this case, overflow is a 0. So have you noticed a pattern? When the overflow is happening, the sign of the difference is telling you the opposite of what is supposed to be. But if there's no overflow, then we can just rely on the sign flag of the difference. So are we observing that pattern? We are. Okay, very good. So now we're going to create a truth table. So the truth table says, okay, let's take a look at d of m minus 1, which is also known as the sign flag. Okay, we look at the overflow. Do we have an overflow? And then we come to the conclusion of, so in that case, is x really less than y? Okay, so we're going to create a table like this. So there are only 2 of these, and then 2 of those, and then 0, 1, 0, 1. Okay, so remind me again, when overflow is a 0, can we trust the sign flag? Yes. Okay, so that means for these 2 rows, we just copy 0 and 1 over here. Okay, cool. So that means when the overflow is a 1, then we have to flip whatever d subscript m minus 1 is, because when we have an overflow, the sign flag of the difference will tell us the opposite of what it is supposed to be. So this gives me a 0. We have to turn that into a 1. And this is a 1. We have to turn that one into a 0. So what are you observing? Does this truth table, if you just look at the zeros and ones, okay, forget about the heading. If you just look at the zeros and ones, does that remind you of a particular truth table that we have seen at least twice up to this point? The R function, exactly. But the R function can also be done using a logical operator. Which single operator is that? Exclusive OR. Very good. So that tells us that, oh, okay, so if we just take the exclusive OR between the sign flag and the overflow flag, then we have the answer that I call the L flag. L stands for less than. Okay, so that's how the L flag is determined. So we only got one more thing to do is, but how do we determine whether there's an overflow or not? So now we have to take a look at overflow. Okay, so I'll let you guys copy this down first. It is in the notes as well, but once again, it's nice to kind of put all the definitions and all the conclusions in one place of your own notes. So, so after this, after you guys write this down, then we'll be looking at the overflow flag. It's like, how do we know whether there's an overflow or not? Are we good so far? All right. So I'll put it on this side here. Okay, so we'll focus on the subtraction. Okay, so subtraction, subtraction. And we don't really care about the entire subtraction other than what happens to the most significant bits. In other words, we only focus on x subscript of m minus 1, y subscript of m minus 1, and then d subscript of minus 1. Those are the only three that we need to take a look at. Why? Because we can tell by the sign alone whether there's an overflow situation or not. Okay, so we'll put this on another truth table on the following page. Are we ready to move on? Because I have to flip a page. We good? All right. And I'm just double checking that we are still recording. We are in fact recording. All right. So now we take a look at x subscript m minus 1, which is the sign flag of x, otherwise known as the minuend. Okay, this is the value that is being subtracted from. Then we have y of m minus 1. This is also known as the subtrahend. This is the amount that we are taking away from the minuend. And then we have the difference, which you already know what it is. It is just x minus y. And we only care about the sign flag. These three they're not truly independent, but it does give us 8 possible cases. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and last of all, 1, 1, 1. Okay, and I want to know, is there an overflow? Okay, so we are asking, do we have an overflow in this case? So you look at the sign. This means we are x is non-negative, y is non-negative, and the difference is also non-negative. Can that happen? Sure. 3 minus 2 is a 1. They are not all non-negative. So we go like, nope, we do not have an overflow here. Is that okay? So this is what I'm doing on each row is to say, can we have an example of this and does it make sense? Okay, it does make sense. So on the second row, we have a non-negative quantity minus a non-negative quantity, but somehow ended up as negative. Can that happen? Yeah, 2 minus 3 is a negative 1. Okay, that can happen. So it's not an overflow. And then we look at this one. It is a non-negative quantity minus a negative quantity ending up as a non-negative quantity. It has to happen, right? So there's no overflow here. We look at this one, which is a non-negative quantity minus a negative quantity ending up as a negative quantity. Does that make sense to you? It does not. It should not. Okay. So we have an overflow situation here. I don't even care about the rest of the bits. Just looking at the sign bits, I already know this doesn't make sense. There's overflow. Are we still doing okay so far? All right. So now we just complete the table here. This is a negative quantity minus a non-negative quantity, ending up with a non-negative quantity. Does that make sense to you? Nope. So we have an overflow. The other three are actually not overflow because you can subtract. This is a negative quantity minus a non-negative quantity, ending up as a negative quantity. That has to be the case. So it is not an overflow. We have a negative quantity minus a negative quantity ending up as a non-negative quantity. Yeah, that can happen. Negative 3 minus negative 3 is a 1. Okay, it can happen. And then last of all, we have a negative quantity minus a negative quantity ending up as a negative quantity. Negative 3 minus negative 2 is negative 1. Yes, it can happen. Whew. All right. So as I'm going through this table and you were bored because you already know all this stuff intuitively, congratulations. You have a good sense of numbers, okay? Because we are looking only at the sign of a subtraction between the minuend, subtrahend, and the difference. So you intuitively already understand, how those signs are supposed to work out. That's great. On the other hand, if you struggle a little bit with those concepts, it might mean that you have to strengthen your math side of things. Okay, so just a little observation. So now the question is, so how do we make a equation out of this whole thing? Okay, because when you have a table like this, that means okay, tech is going to define OV or the overflow flag using x of m minus 1, y of m minus 1, and then d of m minus 1. So I'm going to use exactly the same trick as before. Yes, go ahead. hmm Okay, that's that will work. Um, but to make it turn it into a Boolean expression, the easiest way to turn this into a Boolean expression, and I'm going to introduce a shorthand at this point. Okay, what looks like a multiplication is a conjunction, and what looks like an addition is a disjunction. So that notation is used by mostly by computer engineers, and I know there are a few computer engineers or a few people here who want to be move on to computer engineering. So this is a computer engineering notation, but it's really specifying Boolean operations. So on this row, I can now say um, we negate x of m minus 1 multiplied by, which is conjunction, m minus 1 conjunction with d of m minus 1. So when you look at this particular expression, it is true, but only for this particular row. It would be false for all of the other rows. Does that make sense to you? Because I specified the exact condition of, oh, x m minus 1 has to be a 0 because the negation will become a 1. Y m minus 1 has to be a 1. D m minus 1 has to be a 1. In other words, this expression itself can only be true if and only if this row is happening. So I do the same thing with the following row, in which case I specify m minus x of m minus 1 not negated, y of m minus 1 is negated, d of m minus 1 is also negated. So this conjunction, the second conjunction, is true if and only if we are on the fifth row of the truth table. But the overflow can happen on both rows, okay? So we just need an or to combine those. So now we can redefine OV or overflow. When I'm writing in the class, I call it OV, but as a flag, which we'll learn later, it's just the O flag. The reason why I add a little V here is because otherwise it looks like a 0. And I don't want you guys to think, oh, okay, that means this whole thing your value is to 0. No, this is an overflow flag. So we are using overflow here. So this whole thing, since I'm really kind of lazy, nope, we need, no, go back. we need a lasso tool so I can copy and paste. Yes, copy, paste, slide it here, and then do a plus, and then use the lasso tool again. There we go. Yes, I cheated. You guys have to write, and I can just copy and paste. All right. So that we can, so now I have translated everything into logical operations. Because here we have negation, exclamation point is still negation, 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 and then we have a conjunction of these three. We have a conjunction of those three, and then we have a disjunction in between. The reason why I switched to this particular notation is simply to save space, because otherwise we'll have to type ampersand ampersand all the time, and then a bar bar, in this place. But this is also what computer engineers use when they want to express logical expressions. So this is kind of a switch, mostly for convenience. All right. So why would anyone consider computer engineering as a major as opposed to computer science? What is the difference? It's focusing more on the hardware side to the logic gate level. So because you're below the logic gate level, you're at the transistor level, that's the job of electrical engineers. So there's a little bit of overlap between a EE and a CE, but most CE only can stop at a logic gate level as opposed to the transistor level. Okay, so in the current context, okay, why are there jobs for computer engineers? What is happening? What is happening with NVIDIA, with AMD, and now with Qualcomm? Hmm? The tariff is one. Yep. So it would be it's good, if the tariff is high enough, it is better off if they manufacture the chips in the United States instead of having to import those chips from, is it S TSMC? So, hmm? Well, they have the monopoly on certain chips, not on all chips. NVIDIA and TSMC has a close tie, but not so much with Qualcomm. So what is happening with Qualcomm? Do you guys keep up with the news? If you were to look up Qualcomm and AI, what do you think you're gonna find? Because those two are usually not associated, right? Qualcomm, you think of cell phones, right? You think of, oh, okay, what is my Snapdragon something, okay, in your phone. Well, Qualcomm is now working with OpenAI to come up with their own chipset for neural network to specialize in neural network computation. Okay, so are they going to just walk over to NVIDIA and go like, "Hey, can I just kind of copy what you have so that I can fab it in the United States?" Yeah, good luck. That's not going to happen, right? In John Wick's words, yeah, not really. Okay, and then somebody dies. Um, no, that's not going to happen. So they have to develop their own chip. Okay, and that's happening. Okay, it is already happening. I think they have already finished the design, and they're gonna fab the chips. So what is the biggest obstacle to these AI data centers? What is the limiting factor? There are two that I can name, but I will let you guys think about it. Yes, the, why are they so expensive? After all, silicon is really just sand. Right. Hmm. So that's also that's a valid reason why they're so expensive. But the so it's not really just that these are big chips and the yield may not be very high, but it's also because of the supply and demand curve. Okay. So what do you think of the supply and demand curve at this point of time for AI chips? So there's a huge demand, but the supply, as you said, is limited. Okay. There are only so many chips they can make per day. Okay. So that drives the price up. Okay. So the price of these AI chips being high is not only because they are difficult to manufacture, but it's also because of the demand. I think Jensen Huang from NVIDIA, he said, he had to decide who to sell the chips to because everybody is taking suitcases of cash and go like, I want 2,000 of these things, you know, and they go like, but I have to decide who to sell it to, so that's the reason, okay? And this is also the reason why OpenAI is going like, I don't want to play this game, and he's going to Qualcomm and say, let's go ahead and make our own chips so that I don't need to rely on NVIDIA for their chips. So that's happening right now, okay? Now whether this will still be the case when you graduate with a degree in computer engineering, that I cannot tell, okay? So that's one barrier, okay? The one barrier is chip availability. It is so bad, okay, that students who want to study AI or neural net type of AI specifically, they will choose which university to apply to based on whether the university has access to hardware. Because you cannot do research in this area without the proper hardware setup. Okay, so you're absolutely correct. That's one reason. What is the other barrier um, that is limiting how much GPT and stable diffusion uh, stuff we can do? Yes. Hmm. Okay. So let's just assume that all the AI companies are like a certain individual who doesn't care about the environmental impact and also the health impact to other people. So I'm not going to name that person. I think most of you know who that person is. Okay. So let's just say that everybody does not care. Okay. So even with that mindset, there is still a hard limit. What is that hard limit? Hmm? Nope. Nope, not so much the content. So if we don't retrain the neural network and we just go like, yep, GPT-5 is fine, okay, we are good with GPT-5. We don't need to retrain the whole thing. Even with that assumption, we're still running up against a wall. What is that wall? Energy, energy. Okay, you can only even if you don't care about the environmental impact and the impact to the health of other people, energy is still a limiting factor. Okay, and this is also why Google, Meta, and a few other companies, they already have the license to become their own energy producer. They can basically run a generator if they wanted to. And they're also considering going nuclear because you definitely don't want to rely on solar, because if you rely on solar, what about those people who want to use ChatGPT at night? I'm sorry, your ChatGPT is going to be running at 1/10 of the speed when it is compared to the daytime. No, that is not going to fly. So nuclear is the next option, and some of these companies also start to invest money in fusion technology because that's going to be the next big thing in energy production. Energy is the other barrier. So why would a computer engineer be related to this whole discussion of energy as a limitation? Okay, you go first and then you go ahead. Okay, all right, go ahead. Hmm. Hmm. Yep, exactly. Yep. Because the energy dissipation within a confined space is also another limitation. Even if you have an infinite number amount of energy, the amount of energy you can dissipate from the facility is still limited. So they're hitting a lot of quote unquote energy related walls. So even if you can pump energy into the facility, well, most of that energy converts to heat. So you still have to dissipate all that heat. So, yep. So that's why computer engineering is getting kind of more interesting now because there's a certain demand to improve the efficiency of these AI chips. So I hope this is helping you to kind of evaluate or re-evaluate. Do you want to transfer to a CE or a CS program? There's another one, I know we are kind of digressing here, but I think it's kind of important. Another thing that's on the horizon, but not quite as glamorous as AI, is quantum computing. It's quietly progressing, quote unquote, in the background, but it is actually far more important, even compared to AI technology, because quantum computing can fundamentally change the way we perform computation. So, if you want to pursue quantum computing, what is going to be your major? Physics would be good, okay? Physics maybe with a minor of computer science, or math and computer science, okay? Because quantum computing relies on the fundamental math for quantum computing is not it's not in 400, 401, 402, or 410 of the math classes. We don't teach tensor math at this level, okay? But having said that, linear algebra is a good foundation to get to tensor math, which is then needed for quantum computing. So that means, if you want to get into quantum computing, having a stronger math background, especially in linear algebra and tensor math, that is actually useful. So I just want to give you guys all this information, because um, a lot of things are happening. Okay, they're changing. Um, so having more options is always good. All right. So now we have everything that we need. Okay, because we have the getting back to what we are talking about here. So we got the overflow, and then in the previous slide we have the sign flag is easy because it really is just the most significant bit of the difference. We now know how to compute this. So now we can also compute the L flag. So in the notes, I just want to relate it back to the notes because that's another green section that you probably the only portion that you really need to understand is this portion here. So the overflow flag is defined as this, okay? Exactly the way we defined it earlier. And then we also come to the conclusion that the L flag is a 1 if and only if the sign interpretation of a bit pattern X with up to m bits is less than the sign interpretation of Y up to m bits. So that is the conclusion. And this is why it is in a green box, because it is the important part of this entire discussion. So now between the L flag and the borrow flag, the overall borrow flag in the subtraction, we can now determine whether x is less than y. The borrow flag is useful for unsigned comparison. The L flag is useful for signed comparison. They are different. This might remind you of a certain thing that we talked about, which is, hey, signed versus unsigned, the same. We are adding the same way, we are subtracting the same way. So what is the difference? Why do you care? Because when you compare, they are different. When you compare, if you're using VS, which is the sign interpretation, you have to look at the L flag to know whether X is less than Y. But on the other hand, if you're doing the unsigned interpretation, then we go all the way back to the beginning and we say, oh, okay, if you're using the unsigned interpretation, then all you need is the borrow flag. The most significant digit of the borrow flag will indicate whether X is less than Y or not. So that's essentially the most important part of the takeaway of today's class. And we still got 4 more minutes, so I'm going to have to yak for 4 more minutes. So I'm going to ask you this. So if I can just give you the green boxes and be done with it, this class would have been done in 15 minutes. So why did I waste all that time to give you all the examples and ask you to notice the patterns and also to go through the math stuff to explain all of that? Hmm? Do you? Okay, so how about this? I will switch around and say, do we know what this is saying? And that's basically what I said. So when you have an unsigned, if you have an unsigned comparison, then the most significant bit of the borrow indicates whether X is less than Y, which is exactly what this is saying. Tm of 1, Tm equals to 1 if and only if the unsigned interpretation of X is less than the unsigned interpretation of Y. That's exactly what it is saying. So why? Why did I take you on a scenic route when I can just say, hey, this is the shortest route between those 2 points, but instead I took you through the park. Is that important? And why is it important? I'm showing you how I reason through the things, right? How I reason out, why can't we just look at the borrow flag? Okay. Now, if you ask, how do we make this determination? Many textbooks will tell you right away, oh, just look at the borrow flag. Or how do we compare signed in the signed interpretation? It will just give the conclusion that we also arrived at, right away. But how do we get that? Okay, why does it work? Okay, those things are important to me, and that's why I include all of those things in the OER. Okay, this is called OER, which stands for Open Educational Resources, which means this is not coming from a textbook. I did not copy and paste from anything, not even Wikipedia. This is all mine. It's because I cannot teach anything until I understand the principle, the how and the why thoroughly. Okay? That's how I teach. This is how I acquire information and learn things. Do you think that's going to be useful in your case? Because I don't have to contend with AI, when I entered the industry. Okay, it's like pretty easy. You guys have to contend with a lot of things. Okay, AI is one of those. So even if AI were to stagnate right now at this point of time, it is still capable enough to do a lot of things. So you have to contend, you have to compete with that. On top, many companies have already laid off their entry level and mid level software engineers. Those people are still floating around looking for jobs. Okay. And I don't think, in another 2 years, those people will either transition to a different occupation or would have employment. So you might still be competing with those people, the people who are mid-level or entry level today, and they got fired from these larger corporations. So you might still be competing with those people. Okay, so how do you outcompete those people and AI? Well, you have to be good at reasoning. Critical thinking, reasoning, analysis, those are the really important soft skills. All right, well, I think I've preached enough already, so we will move on to your lab activity for today. And some of you will go like, oh man, that is boring. Because today's your lab is really just recreating the 3-bit by 3-bit adder. If you recall right away and go like, but Tech, didn't you show us exactly how to do that in one of the classes? Yes, I did. So it is, but you don't have to remember, okay? I'm not relying on you remembering the whole process. This lab actually will take you through the whole process too. So it is more or less a review of things that I have done already. So you can now go to the activity. It's called 3-bit adder. It is the same thing. It's the same 3-bit adder in terms of the concept as what we did, the other day. The access code is 3x3. So I'll put it on the whiteboard. There we go. And I believe it is already open because it's 10:21. I opened it at 10:20. So with this one, for people who do not really want to read the instructions, they can watch the recorded video from, I cannot even remember. It's not the previous class. I think it's a week ago, 2 classes ago. And I went through the whole process in Logisim. So if you're recalling that, that's good. If you're not recalling that, hmm, uh, yeah, you might need to pay more attention in class. All right, so can you guys get into the activity? Okay, great. So I'm gonna step out of here, get some water to drink, and then I'll be back. Right. Oh, I can turn off the recorder.